Okay, welcome to this deep dive. We are jumping into some source material you shared. It's Calculus for College Students, Nutrient Uptake Modeling.
That's right. And our mission, really, is to unpack how this specific text uses calculus. We're talking differentiation, integration,
Yeah.
to understand something, well, really practical, how plants actually pull nutrients out of fertilizer over time.
This sounds perfect if you're, working through calculus yourself and looking for that kind of concrete link, seeing how these math concepts actually describe real-world stuff.
Absolutely. It's all about that connection. So let's see what your source highlights there.
Okay, so the material, it seems to dive right into modeling the rate of nutrient uptake first off, and it mentions using derivatives for this.
Right. And what's fascinating, I think, is how the source likely uses differentiation, not just to state that a rate exists, but to really describe how that rate changes.
Oh, okay.
Because a nutrient uptake, it isn't usually just a flat, constant speed, right?
Yeah, that makes sense.
According to your source, it probably follows some kind of curve. Maybe it peaks relatively quickly after you fertilize and then, slows down.
Okay.
And the derivative, well, that lets us pinpoint that peak rate, understand the dynamics kind of moment by moment.
So instead of just knowing, like, eventually how much nutrient the plant gets, we can understand the intensity of the uptake right now. And the sources model gives us an actual function for that.
Exactly that. The source probably presents a function, let's maybe call it RT, where T is
Right.
time.
Right.
Then RT, the derivative, that gives you the instantaneous rate.
R prime of t. Got it.
Yeah. And the text might even discuss what shapes this function could take. Maybe it's influenced by um, factors like soil temperature or moisture levels,
Mhm.
parameters the model folds in.
It makes a lot of sense, actually. Understanding when the plant is taking up nutrients fastest feels pretty crucial for, well, growing things.
Yeah.
But what about the total amount, the accumulation over a whole growing season, or maybe between fertilizer applications? Is that where the other pillar of calculus comes in?
Precisely. You anticipated
Yeah.
it. So if RT is that rate function described in your source,
Yeah.
then to find the total accumulated nutrient uptake over some specific period, let's say from day 0 to day t, you'd integrate. You'd integrate that rate function over that time interval.
Ah, okay. So the source uses integration to basically like sum up all those little instantaneous rates over time to get the grand total?
Yes, exactly. It connects the speed of the process,
Yeah.
moment by moment, to the overall outcome. The source might even use this integrated value, say, to compare different fertilization schedules or different nutrient mixes.
Oh, interesting.
Yeah, calculating which approach, at least according to the model, results in the highest total uptake over some critical period for the plant.
Okay. So the source isn't just saying calculus is useful in a general way. It's actually providing a framework using specific functions, maybe parameters,
Yep.
to model this biological process.
That's really the key takeaway, I think, from this material you shared. It moves beyond just the abstract definitions. It shows a very specific application, using differentiation to describe the dynamic rate of uptake,
Okay.
and then using integration to quantify the cumulative effect. And the details in the source, about the likely form of the right function or what its parameters mean, those are the specific nuggets that make this application really concrete.
Right. So stepping back, what does this all mean then? This little exploration into your source material, it really shows that the calculus concepts you might be grappling with, they aren't just theoretical exercises, are they?
Not at all.
Using derivatives to model the rate of nutrient uptake and integration to find the total amount over time,
Hmm.
well, it provides a powerful quantitative way to understand these essential biological and agricultural processes.
It really does.
That kind of makes you wonder, doesn't it? What other dynamic processes out there in nature, maybe things like disease spread or resource depletion, could be effectively modeled and maybe better understood using these same calculus tools you're learning right now?